Hello, Strange Loop. I'd like to talk to you about distributed column stores and why we built one. I'm Sam Stokes. I'm an engineer at Honeycomb, which is a small startup in the San Francisco Bay Area. There's a few of us in the crowd. When I'm not making software, I'm usually making cocktails and sometimes bad jokes. And I'd like to introduce you to Retriever. What is Retriever? Well, Retriever is a distributed column store. It's also an analytic query engine, and it's got a schemaless data model, and hang on a second. I'm really getting ahead of myself a bit, because you're probably wondering, why would someone build their own data store? It's pretty much rule one, right, that you don't build your own database. And if you do, you especially don't call it a database. You call it a data store, which is why we built a data store. So Retriever is a special purpose data store that we built to power Honeycomb. And so to talk about Retriever, I have to explain a little bit about what Honeycomb does. Well, you can think of Honeycomb as a debugger for production systems. What does that mean? Well, we want to help engineers understand and troubleshoot distributed systems. As you might be aware, especially if you've been to any other talks at this conference, distributed systems can be kind of tricky beasts at sometimes. So Honeycomb sits in between sort of traditional metrics tools and traditional log aggregation tools. That's a bit abstract. So let me make it a bit more concrete. How does Honeycomb work? Well, your systems, the ones you want to understand better, they send us events. Events are kind of similar to structured logs, if you're familiar with that cool buzzword. They're also JSON blobs. Here's an example event, and this represents a server processing some kind of web request. So you'll see events have a bunch of fields. This one has like an endpoint field, what endpoint on the web app was being hit, the host name that processed the request, some statistics about response time, and so on. So you send us events. We store your events, and you can ask for them back. And then you can issue queries on those events. And the reason you might want to do that is you can ask us to calculate things. For example, here, we're saying for every endpoint that events have come in for, calculate the average response time that we spent processing the request for that endpoint. And we're going to visualize something else, the amount of time that was spent in the database processing those requests. OK, so we take your queries, and we turn them into pretty graphs like this. There's a lot going on here. So at the top graph, I'm kind of showing this is the average response time for every endpoint. And the bottom graph, this is a visualization called a heat map. So don't worry too much if you aren't familiar with heat maps, because that's not what this talk is about. But heat maps are a pretty cool way of visualizing the distribution of response times. So if this is time spent in the database, you can imagine that these two bands are sort of showing, here are some requests that hit the database cache, and here are some that missed and took longer. But the idea is, so we can draw graphs, and graphs are awesome. Graphs help you look for patterns and detect anomalies. But we want you to be able to always jump back and forth between the graphs of the calculations that you've drawn and the raw data that came in, that you sent us, that we generated those graphs from. And what that lets you do is you can find something weird on the graph, and then you can say, well, hang on, why did that happen? What was actually going on there? And you can go back and look at the real event with all of the data that you sent us and all of the detail, and look for signs of weirdness. And there are some other questions you can ask this kind of system. An example is, which of your users are seeing the highest response times? So this isn't a question about the global average response time across the whole site. This is saying, literally, for each user, find the ones that are seeing bad response times. And you might express this in a query, something like, show me the average response time broken down by user ID and ordered by the average response time. What about I'm running a deploy, and my deploys roll out gradually across a fleet of servers, and I want to know how many servers has my deploy got to? Well, I can express that in this kind of system if I'm tagging my events with a build ID. And so then as events are processed, I can say, show me the number of unique host names that have sent me events for each build ID. And you could kind of see the new build trending upwards as the deploy rolls out. What about for all of our customers who are on our most expensive pricing plan? Are any of them affected by this error we've just been troubleshooting? And the idea there is, at the point when you're sending us an event, maybe you're consuming some logs, maybe you've instrumented your code, but the person who's doing that work doesn't want to care about which customer is high value. They don't know about who's on which pricing plan. They certainly don't want to have to update their code when a customer changes pricing plan or you sign up somebody new. But it's still a really useful query to be able to ask if you have some other representation of which customers are on which plan. And so the idea is we need to be able to query really flexibly on the data that we've got. Well, how do we do that? So what do we do with all the data that you're sending us? How do we store them in a way that we can serve those kinds of queries and get graphs out? Well, spoiler alert, the answer is retriever. So for the rest of this talk, I'd like to describe to you what it was like building retriever and some of the decisions that we made. I'll start with a pretty high-level overview of what it looks like and how it works. I'll dive deeper into how we store the data on disk and how we read it back, and especially some of the details of how we read it back really fast when it's spread across multiple machines. And finally, because this is a database we run in production, data store. This is a data store we run in production. Remember, don't build a database. We run this for paying customers. So there are some interesting things we need to do to make that actually work in the face of the real world. So what do you need in a data store that can serve this kind of features? Well, we need to issue queries. And we have a fairly flexible sort of query model. So we have these operations like breakdown, saying take the events that you've sent and break them down by the value of some field, like breakdown by endpoint or breakdown by user ID. And you can filter, which is discard things that don't match the filter. And we want you to be able to break down and filter by any field. You don't have to say in advance, I'm only going to break down by endpoint or I'm only going to break down by user ID. You can make up your mind afterwards. And so you're not predefining an index or setting up a schema and then having to comply with that. We need queries to be able to produce two different kinds of results. So we have time series graphs, and in fact some weird and wonderful visualizations like the heat map thing as well. And we also have queries that can return just the raw data that came in, according to some filters. And we need to calculate the kinds of statistics that are useful for operations purposes. Really, that's what we're trying to solve here, is the sort of problems that operations people face. So percentiles are really useful for latencies. If you're still measuring average latency, you should really try percentiles. We can calculate the histogram for an entire distribution of response times or of packet sizes or of other things like that. Count distinct is another really useful operation. We need all of that to be really fast. And the reason for that is we want users to be able to do a sort of question and answer workflow with their systems. So something goes wrong. The user forms a theory about what went wrong and why. So they ask a question. For example, is this only happening for certain users? They ask a question to test their hypothesis. They get an answer back, and maybe it confirms the hypothesis, in which case they might want to refine further and drill down. Or maybe it turns out the hypothesis was wrong and they need to try a different tack. And in both of these cases, it's really important for the Q&A to be really fast. You don't want to sort of set a query running and then go have a cup of tea and then forget what you were doing. We're running this for multiple customers, and so we need to be able to do things like enforce quotas and other properties that are tied to our business model. And so we need some sort of custom tools that can manage that sort of thing and let us go in and poke a customer and change their quota. And maybe most importantly, we're a startup. We have an extremely limited budget and an even more limited team. An awesome team, but a limited one. So this thing needs to be very simple. We are not building a general purpose database here, and we don't need to. We know exactly what data is coming in and at what rates, with what access patterns. We control the query interface, so we know what kinds of questions can be asked of our data. So we have this very precisely defined use case. We can write a special purpose data store. We also don't need to support updates, because once an event's come in, it's happened already. You don't need to go and change it. And we don't need to support the kinds of fancy features you would get in a more general purpose data store, like joins or transactional semantics. So we need to keep it simple. So again, we need to issue all kinds of queries really quickly and not spend hundreds of person years doing it. So what does a system look like that can handle this sort of workload? Well, it turns out someone already built one. It's called Scuba. Scuba is a system that was built at Facebook. They released a paper on it called Scuba Diving into Data at Facebook. And this being Strange Loop, there's a pretty high chance that one of these 12 people is sitting in the audience somewhere. And Scuba was built to solve exactly the same problem because Facebook has this problem as well. They operate very large systems at scale. And so they built a distributed event store. And the idea behind Scuba is you ingest events at very high volume from lots of producers, lots of systems at once. And you store them all, every single event, and you store them distributed across many servers. And that lets you scale out the amount of stuff that you're storing. And it also lets you speed up queries, because when you want to query the events, you can fan the query out across all those servers and do a lot of the processing in parallel. And then to make things even faster, they take those events and they store them in RAM, which is ludicrously fast, obviously. So the problem with Scuba is it's a Facebook tool. We can't use it, which means our customers can't use it. But we can be inspired by it. They were kind enough to write a paper about it. So we thought, well, what if we could build a really simple system that's inspired by the design of Scuba? So Retriever is similar, inspired by Scuba. We are a distributed event store. We store the events that come in distributed across servers, and we get fast queries by fanning out the queries to multiple servers. But we do a few things a little differently from Scuba. And the most important and obvious one is we store data on disk. And the reason why we store data on disk rather than RAM is because we aren't Facebook and we don't have the infinite money cheat code. It turns out that RAM is expensive. And it turns out that SSDs are really fast. And especially if you can do certain things with your access patterns, you can actually get really fast queries just by reading from SSDs. Also, file systems are pretty good at caching stuff these days. Because we're storing data on disk, that means we can also depend on the file system for a lot of the semantics that we need from our data store. And that's pretty useful. It means we can do something called column-oriented storage, which some of you may be familiar with this already. I'll be doing a recap of that later. For you, it'll be more of a recap, but I want to make sure everyone's on the same page about that. And we use Kafka, which I'll talk about more later, for ingesting events. And that gives us all kinds of cool operational properties which we can rely on. So some of you may prefer to see a map of the territory before you go on a hike. So let's do a quick overview of what writing and reading looks like. This is the architecture of Retriever. A customer sends events. They are published to a Kafka topic. If you're not sure what that means yet, I'll cover Kafka later, but I'm sure a lot of you are. So we publish events to Kafka. Retrievers consume from Kafka. They receive all the events that come in and write them to disk. And we have retrievers operating in pairs like this. And then to read, a query is issued by our API. It's going to pick a retriever to run the query. It'll issue the query to that retriever. That retriever will fan out the query to other retrievers that have the data it needs. They'll compute the results and send them back. Awesome. Well, that was extremely high level. Let's explain how some of that actually works. This is a picture of, this is a column-oriented picture, by the way. I did warn you about the bad jokes. So our data model is that customers have one or more data sets. And data sets, you can think of them as basically tables in a traditional database. Data sets are partitioned across multiple servers. Each data set is assigned to a number of partitions. Typically, we have about 3 partitions per data set. Our largest data set right now is sitting on 39 partitions. And those data set partitions contain events. We've met events before. Let's recap. So here are a couple of different events. These are both processing web requests. And so you see these 2 events have a slightly different shape. The second event has this error field. But that's the idea. Events are just JSON blobs. You send us lots of them. So I'd like to visualize these events in a slightly different format for a reason that will come apparent very quickly. So I've drawn these events in a table. And what we've got here is, in a fairly traditional way, I've got the fields of the events in the columns of the table. And then each row is one event. So here we've got 5 events showing a few requests to the foo path and some to bar. And then we have this one other event that has none of that data and just has like a log message in it. And the point about this is there's no schema attached to a data set like you might get in a traditional MySQL type database where each table has a data set, has a schema. So you can send us events of all shapes and sizes into the same data set, and we'll just happily store them. We're not going to say, like, this one is the wrong type for this data set. And events can have an arbitrary number of fields. We have some events with hundreds of fields, and that's actually a pretty normal case. You might be thinking, well, why the hell would I have an event with 100 fields in it? Well, let's imagine these events are representing the processing of a web request. And there's already some stuff I've left out here just for space. So we've got the path, we've got the response time to process the request, we've got the status code. But I don't have the host name in here. I don't have the headers of the request. Maybe those are useful. Maybe while you're processing web requests, you want to log how much time you spent in the database for each request. That'd sure be useful to know if your database starts running slow. Maybe you want to include application-level information, such as the user ID that the request was for, or maybe something more specific like, when we did this particular database call, it returned this many rows. And so you can imagine if you have these really rich events annotated with lots of data, they can have quite a lot of fields, but not all of those fields are going to be populated all the time. And that's what we see here, that all of these fields can potentially contain null values. And a couple of columns I'd like to point out. So we have this index column on the left. We assign every event an index as it comes in. And that's going to come in later. But the idea is these are unique for each event. And every event has a timestamp. Kind of by definition, an event is a thing that happened at a time. So that's just the time the event happened. OK, so how do we store these? We have a few choices, because what we need to do is take these structured events and store them on disk as files. And files are just streams of bytes. So we need to take this structure and serialize it somehow. And broadly, we have 2 choices about how to do this for this sort of data. We can serialize it in what's called a row-oriented way, or what's called a column-oriented way. So apologies if you already know about column-oriented storage. This part is going to be very familiar. So row-oriented is sort of a traditional choice. This is what a lot of databases do. What I've done with the table here is I've cut out some of the fields and focused in on just a few events, just for simplicity. So the idea behind row-oriented storage is you store everything pretty much in one file. And you take all of the fields for a given record, a given event, and you just lay them out on disk next to each other. So one event comes in. We're going to store the fields. We just got the path and the response time and the status, and then a nothing for the error. Another event comes in. We do the same thing again. Another event comes in. So we store this stuff sequentially. And a couple of things to point out here. One is this empty space that we have to leave if there's a null value. And there's a few different ways you can encode this, but most of them you have to somehow indicate that, hey, there'd normally be a record here, but I don't have it in this case. And that's one thing if you've got one null value, but if you have 100 columns and most of them are null most of the time, that's actually kind of a lot of wasted space just to say that there's nothing there. And the other thing, the way you read this is you read a whole record, and then you read another whole record. And that's great if what you're doing is mostly reading, if that's what you mostly want to do, to get the entire contents of a record. And in a lot of like ORM use cases, that is what you want to do. You just want to load your user object into memory and then do stuff with it in the application. But if you're only concerned with a couple of these fields, you're actually doing a lot of I/O that you don't need. So an alternative way of serializing data like this is called column-oriented. So I've expanded the table again to include those index and timestamp fields because I'm going to need them. The idea of column-oriented storage is instead of storing all of your events in a single file, you make a file for every field in the events, otherwise known as column. So you have a file per column. So here's how we would store, as an example, the path field. We have a file called path.string because it's a string. So an event comes in with index 0. We write the index value, and then we write the value of the field, which is foo. Another event comes in. We write the index, we write the value of the field. Another event, same thing. So this is how we would encode one column of this table. Just to hammer home the point, here's how we would do it for the response time field. We write the index, we write the value, and so on, and so on. So you might be wondering, well, how do we do this when there isn't a value to write? So for the error field, the first event that came in didn't have an error, so we just don't write anything. We're not even going to create this file, in fact, until we have a value to write. So the next event comes in, and we do have a value, so we just start at the index 1. We write index 1, we write the value. Next event has no error. You get the idea. We don't write anything. So this is the whole column file for error. And imagine there were 100 events that came in and only one of them had an error. You'd only have written one value there. The timestamp column that I mentioned earlier is stored in a very similar way. We write the index, we write the timestamp. The reason this is worth looking at is because the timestamp is guaranteed to always be present, we can use this column also as kind of an index. In other words, this tells us what indexes exist. And because every event has an index, this tells us what events exist. The reason we double up the index and the timestamp like this is because almost all your queries are going to be based on events in some time range. And this lets us do a quick filter against timestamp. But we can talk about that later. So how do we read data that we've written in this slightly awkward kind of way? Well, we don't just have one file to read anymore. We have potentially a variable number of files. So the first question we need to ask if we want to read is what files do we have? What columns do we have available to scan? Well, these are just files on disk, as I said earlier, which means we can basically just run ls. Like we can ask the file system, what files do you have? So in this case, it might say I have path, response time, status, and error. Let's say we're calculating the average response time. I know I just told you all to do percentiles, but this is an easier example. Let's say we want to do the average response time for events that have status 200. And let's go through how we would read that. So first, we need to open the files that we want to read. Well, we can figure out what files we're going to need by looking at the query that we're trying to run. So we're going to need the index file. Because we always need the index file, we need to know what events there are, otherwise known as the timestamp column. We're going to need status because that's what we're filtering on. So we need to check if the events meet our query. And we're going to need the response time column. So let's open all those files. And you can think of this star as like a file pointer. So we're going to be reading through these files. So the first thing we do is read an index to find out if is there an event to read. Well, we got an index, it's index 0. Now we need to check the filter. So we'll read from the status file until we hit that index 0 that we just read. Well, it just so happens that's the first value, so we get there straight away. Now we have the status value, we can check the filter. Does it match? Yes, it does. So we read from the response time file until we hit index 0 again. Will we find it? So we save that value for later, and we'll do all the calculation at the end. Then we start again. Read an index. It's 1. Read from the status file until we hit index 1. Here we go. Check the filter. Well, this one doesn't match, so we can skip this event. Start again. Read an index. Index 2. Read from the status file until we hit index 2. Here we go. It matches. Great. Read from the response time file until we hit index 2. Well, hang on. This is index 1. That's not what we're looking for. Well, that's because this is the event that we skipped because the previous status didn't match. So we just keep going. Here we go, index 2. So we forget about that 23. We don't want that one. Here we've got the value 657. So we collect that, and so on. And so this is how we scan through all of those files. And we can do all these reads in parallel so long as we have enough I/O capacity. So let's jump back to the table view to sort of show what it was that we just did. So I've highlighted all of the values that we looked at. So we opened these files, and we read these values, and we skipped over one value in the response time column. But what we didn't do is go anywhere near the path file. We didn't touch the error file. If there were 100 other files, we didn't touch them either. So we read all of this data without reading most of it. This is kind of the mantra of column-oriented storage, is only read what you need. And this is why it's so nice for these analytical queries, because most of those, who's going to run a calculation on 100 fields, right? Like what would that expression even look like? Okay, so we've got some data on disk, and that's how we can execute a query against a single node. Because everything I talked about is reading from files on disk. But this is a distributed data store. So the data exists across multiple nodes. So how do we run that query across all of the nodes? Well, a client's got a query to issue. Let's say it's the same average query. So the client knows what data set it's querying for. So it's going to check what partitions that data set exists on. And then the partitions have retriever nodes listening on them. The client's going to pick one retriever to be the root for the query. And then it sends the query to that retriever. And the retrievers know what other retrievers exist on that partition. So the root node will forward on the query to the other nodes on the other partitions for the same data set. And then they can all scan their data on disk in parallel. And they can all do they can compute part of the answer to the question. And then they can send their partial results back to the root. And the root merges the results and sends them back to the client. And then we have our answer. Well, that sounds simple, but there are a few things we need to watch out for. So the data is partitioned, which means every node only has part of the answer. And there are a few things we can trip up there. We need to be careful in the way that we combine those partial results so we get the right answer. So here's an example. If you're computing an average of a set of numbers, you can't split that set of numbers into two sets and average those sets, and then average the averages. If you do that, you'll get the wrong answer. I don't know if this is entirely readable, but say you're computing the average of 1, 2, 3, and 3. The answer is 2.25. If you split that up into 1, 2, 3, take the average of that to get 2. And then the average of 3 is 3. And the average of those two is 2.5, which is different. So instead, we need to make sure that the way we're computing the partial results is something we can send back to the root in such a way that the root can combine those results and get the right answer. So for an average, you can do it if you compute the sums of the partial data and the counts of the partial data, and then send both of those back. And then you can add up all the sums, add up all the counts, do the division, and get the right average. So we have a few different types of calculation we can run. And we need each of these calculations to work in this way so that we can do a distributed query and get the right answer. So some other examples, if we're calculating values for different groups, so this is our breakdown operator, we're basically going to accumulate the answers, so the statistics for each group in a sort of map structure. And each node can compute its own groups and its own values, then send the groups back to the root, and the root can do the merge. And so long as the values in the group are mergeable, then you can merge appropriately. For count distinct, we don't do this by collecting all the unique values, because that would be really memory intensive, but there's a trick called hyperlog where this is again, this is not what this talks about, but hyperlog is a way of estimating the number of unique values in a given set. And it turns out that hyperlog is a data structure that you can actually send across the network, and it combines in this way. Similarly, for percentiles, there's a probabilistic trick called tdigest, which combines nicely. And this is a property called commutativity, which comes up a whole lot in distributed systems. If you've seen any talks about CRDTs, that's another place where this sort of pattern comes up. There's one more problem we need to deal with distributed queries, which is we have this root node that's merging all the results. But that might be a lot of work. If we've fanned out to 10 nodes or 39 nodes, and maybe those partial results are all of the groups we were collecting, and maybe we have a lot of groups. You know, if that's user ID, you might have 1 million user IDs. You might have more than that in certain cases. And so we don't want to overwhelm the root node, you know, run out of memory or just spend too long computing. It's kind of a shame if we've done all this work to distribute the query and then we still have one guy doing all of the computation at the top. So we can sort of do this recursively, and if we have more than a certain number of nodes that we're querying, we just have the leaf nodes also become roots, and they do their own distributed query pattern. And then because we have the commutativity property, everything rolls out nicely. All right, so we can write data and we can read data. So we're done, right? Ship it. Well, we kind of have to run this thing, right? We have customers, they pay us money. This is the real world. Nodes fail. So we do have to solve a few more problems. So let's talk about how we do that. And I need to embark on a brief detour on this hike to talk about Kafka. Can I get a quick show of hands? How many of you are familiar with Kafka? Wow, everyone in the room, practically. How many of you are using Kafka in production right now? About half the room. Cool. All right, well, I'll skate through this reasonably quickly then. All right, so Retriever relies pretty heavily on Kafka for ingesting our events. So as we saw at the start, events go in through Kafka. Kafka gives us lots of nice properties. It gives us the ability to distribute writes out across multiple nodes. It gives us replication kind of for free. And we rely on it for fault tolerance and disaster recovery. How exactly? Well, as all of you probably know, Kafka is a distributed log. It's not exactly like a message queue, but you can think of it that way. You publish messages to topics, which are, again, kind of like tables. Topics are partitioned, which is the unit of scaling. And within a partition of a given topic, Kafka guarantees that messages are totally ordered, which means messages will come out of a topic partition in the same order that they went in, which is really useful. And Kafka actually stores the messages on disk, whether or not anyone is listening to them. It's not, a lot of message queues will just, when a message comes in, they'll route the message straight to any consumers, and if there's no one listening, they'll just drop the message on the floor. But Kafka writes everything. And you can use that for a couple of things. You can get a sort of publish-subscribe semantics, because the data is just sitting there. Anyone can read it if they like. You can have multiple readers. And it also means you can go back in time and replay messages from some point. So how do we use this? Well, clients publish events to a Kafka topic. and the Kafka topic is partitioned, and our datasets are assigned to partitions. So this is the partitioning I was talking about earlier. We have a number of partitions on the Kafka topic, and the datasets know which of those partitions they are assigned to. So the client, who's writing the data, chooses one of the partitions for the dataset. And right now, it just does that at random. It turns out that random partitioning is actually pretty good for this kind of behavior. So what that means is the client's just randomly writing data between all of the partitions on a dataset. And then we have retrievers consuming from Kafka on each partition and writing events to disk. And because Kafka lets us attach as many subscribers as we want, we just have 2 retrievers consuming each partition, and that gives us replication for free. Because Kafka is guaranteeing that the events are coming in, or the events are coming out in the same order that they came in, then we know we're going to have an exact copy of the data on 2 different nodes. And that's pretty useful. So one problem we need to solve, part of our business model is to price based on storage. So every customer is paying for a certain amount of storage. They have a quota. And we're not in the business of just storing data forever, collecting infinite amounts of it. That would not be useful. So when a customer is nearing the edge of their quota, we want to start aging out the oldest data that they've sent us. Well, this is where we can rely on the file system to do a lot of the work for us. So as events are coming in, we split them up into segments. And you can think of these as sort of time slices of the data coming in. So at some point, we decide we've written enough data, enough events into this segment. So we start a new segment. And because we have just files on disk, we represent segments just as directories in which the files live. So when it's time for a new segment, we just open a new directory and start writing the files into that directory instead of the old one. The old one sits where it was. Which means when we need to calculate how much space a customer is occupying, we can calculate how much space each segment occupies. Again, we can just ask the file system, hey, how much data is in this directory? How big is this file? And when we need to delete data, we can just say, hey, what segments are there? List the directories. Find the oldest one. They're numbered numerically, so we can just sort them. And just delete the directory containing the oldest data. We didn't need to do any kind of in-memory manipulation and worry about concurrency. What about fault tolerance? So this is the big bad world. We run on EC2, nodes go down, processes crash. So why might Retriever crash? Well, we might have a bug. We might have a network outage, which means it's unable to connect to Kafka. We might just be deploying this. This is a piece of software that we're actively working on. We need to deploy to it. We need to take the process down. We have 2 replicas of the data, so that should be fine. But we don't want to miss events as they're coming in. Customers are always writing data. We don't want to just drop those events on the floor. And we don't want our 2 replicas to get out of date. So what we do, and this is another thing where we can just use Kafka to pretty much solve this problem. So each retriever tracks the Kafka messages have what's called an offset associated with them. And that's just how far, as it's writing on disk, how far it's got. And so offsets are auto-incrementing. So as every event comes into retriever, we track what offset it came in with. And when we boot up retriever, we just say, hey, the last event I saw had this offset, so give me everything since then. Kafka guarantees the order, so we know we won't have missed anything. And to make sure that works, we write every now and then a checkpoint file. And that says, here's the last offset that I definitely finished writing to disk. But we need to store something else as well. We need to store the index of the message. And this is the index that we're assigning to the events as they're coming in. So that determines that the offset tells us where to reconsume from. But we have another problem because we're writing to multiple files. And we might have had the problem where we wrote to the path file, for example. We wrote the value for the path. And then we crashed before we got a chance to write the value for the response time or some other field. So we're kind of inconsistent at that point. We've written half the event. And that would be bad, because we don't want to then be returning inconsistent data. So when we reconsume, we look at this checkpoint and we say, okay, this index checkpoint is the last message that I'm sure I finished writing. And anything after that point is suspect. So when we start up, we just take all those files and truncate them at the point where that index is. And so between those two together, we know we've truncated to that point, we're reconsuming from the corresponding offset, so we're going to get all the messages that came since that point, and all the stuff we just deleted, we can continue writing. So that's great, but what if a node goes away completely, like EC2 hosts can just disappear? Well, we have another replica. So we find another node on the same partition, it's got all the data that we need. Now we need to copy the data over to the new node so that it can catch up. Well, these are files on disk. Let's use rsync. And it turns out that rsync is really good at this kind of thing. It can even detect if you've already run, so we can sort of recover from an incomplete bootstrap. Once we're done with rsync, because that takes some time, well, now we're a little bit behind. But that's fine, because we also rsynced the checkpoint file. So we just reconsume from whatever the checkpoint says. Now we're up to date. So that's sort of how we get some of these operational properties. We get replication thanks to Kafka. We get fault tolerance thanks to Kafka. We get quota management by using the file system. And we can bootstrap new nodes using rsync and Kafka. And that is retriever. But what I'd like you to take away from this talk, well, one, column-oriented storage is pretty cool, especially if you're doing a sort of analytical query sort of use case, because you only need to read what you need. Kafka is pretty cool. It basically solves a lot of distributed systems problems for you. So if you're building a distributed system, try not to solve fault tolerance and replication yourself. Those are really hard. Just rely on Kafka to do it. File systems are pretty cool. They have all kinds of nice semantics. They can speed up reads for you. They can do atomic renames. They let you use rsync. But what all that is really a way of saying is sometimes it's fine to solve the really hard problems if that's what your business needs. But make sure first that you've looked for ways to make them easy. Thank you.